Tonight, we are going to walk slowly toward one of the most extreme objects in the cosmos. It is small, only about 12 miles across. It weighs more than the sun, packed into a sphere smaller than a city. It spins on its axis several times every second. And it carries, embedded in its impossibly dense crust, a magnetic field so strong that no laboratory on Earth can recreate it, and no other class of object in the known universe can match it. The object is called a magnetar. The name was coined in 1992 by Robert Duncan and Christopher Thompson, two theorists working at Princeton, who proposed that a particular subset of neutron stars must carry magnetic fields 1,000 times stronger than ordinary neutron stars, and a quadrillion times stronger than the magnetic field of Earth. The objects had been observed for years before they were named. Strange flashes of gamma rays, brief and bright and unrelated to any normal astronomical activity, had been recorded since the late 1970s. Duncan and Thompson identified the source. The flashes were the signature of magnetars releasing energy through magnetic events that no other object could produce. Tonight, we're going to walk through what magnetars actually are, what they can actually do, and why a magnetar at a distance of 1,000 light-years could, under the right conditions, end the habitability of a planet around an entirely innocent star. This is not science fiction. The mechanism is well understood. The energies involved are extraordinary. The actual events have been observed both inside our galaxy and across cosmic distances, with consistent results across multiple instruments and multiple decades of careful observation. Before we get started, sit with what is at stake here. Magnetars are not abstract theoretical objects. There are approximately 30 known magnetars in our galaxy. The closest, called 1E104, 8.1-5937, sits at about 9,000 light-years from Earth. That is far enough that we are safe from anything any current magnetar is likely to do. But magnetar lifetimes are short, measured in only about 10,000 years from formation to magnetic decay, which means that the total population of magnetars that has existed across the history of our galaxy is enormous. Some of those past magnetars must have, by simple statistics, passed close to stars that hosted planets. The consequences for any biospheres on those planets would have been severe. Tonight, we're going to walk through 5 specific things that every magnetar can do that no other object in the cosmos can. Each one is a real physical capability, demonstrated by direct observations. Each one has implications for the broader picture of cosmic violence and the conditions under which planetary biospheres can survive. Each one helps explain why a magnetar represents one of the most extreme objects in the known universe. The 5 things are these. The first thing is that magnetars hold magnetic fields stronger than anything else in the known cosmos. The fields, measured in physical units called Gauss, reach intensities of 10 to the 15th Gauss in the most extreme cases. For comparison, the magnetic field at the surface of the Earth is approximately half a Gauss. The magnetic field in the strongest laboratory magnets reaches about 1 million Gauss. The magnetic field at the surface of an ordinary neutron star is about 10 to the 12th Gauss. A magnetar exceeds even an ordinary neutron star by a factor of 1,000. The field is so strong that it distorts the structure of the vacuum itself, producing physical effects that no other object in the cosmos can demonstrate. The second thing is that magnetars can release more energy in a fraction of a second than the sun produces in 250,000 years. The specific events are called giant flares. They are triggered by sudden reconfigurations of the magnetic field, which release vast amounts of stored magnetic energy in extraordinarily short bursts. The most powerful giant flare ever observed inside our galaxy, the event of December 27th of 2004, released approximately 10 to the 46 ergs of energy in about 0.2 of a second. The brightness of that event, measured at Earth across many thousands of light years, briefly exceeded the brightness of the full moon in gamma rays. Other objects in the cosmos cannot produce comparable bursts on such short timescales. The third thing is that magnetars can crack their own crust through magnetic stress, producing what astronomers call starquakes. The crust of a magnetar is composed of crystalline iron and other heavy elements, packed to densities thousands of times those of the densest materials on Earth. The magnetic stress acting on this crust periodically exceeds the strength of the material, producing sudden fractures that release energy in the form of seismic waves and electromagnetic emission. The starquakes are detectable through specific features in the X-ray emission of the magnetar following the event. They represent the cracking of the densest solid surface in the known universe. The fourth thing is that magnetars can produce fast radio bursts, the brief and powerful flashes of radio emission that have been one of the great empirical puzzles of modern astronomy. Fast radio bursts, first discovered in 2007, were unexplained for over a decade. In April of 2020, a fast radio burst was detected coming from a known magnetar in our own galaxy, definitively connecting magnetars to at least some fast radio bursts. The detection has substantial implications for understanding both magnetars and fast radio bursts, with consequences for our broader picture of cosmic radio physics. The fifth thing, and the one that justifies the title of tonight, is that a magnetar can, under specific circumstances, end the habitability of a planet from a distance of 1,000 light-years. The mechanism is straightforward in principle and extraordinary in practice. A giant flare from a sufficiently close magnetar can deliver an intense burst of gamma radiation to a planet at substantial distance, with the radiation destroying the ozone layer, sterilizing the surface, and triggering atmospheric chemistry changes that persist for thousands of years. The lethal radius depends on the specific properties of the magnetar and the specific properties of the planet, but for the most powerful possible giant flares, the lethal radius extends well beyond 1,000 light-years. 5 things. 5 capabilities that no other object in the cosmos can match. By the end of tonight, you will have walked slowly through each one, with enough detail to feel the weight of what magnetars actually are, and enough perspective to see why they represent one of the most extreme and most dangerous classes of objects in the known universe. Pattern interrupt. The tone of tonight is not panic. Magnetars are rare. The nearest known magnetar is at a safe distance. The probability of a giant flare from a sufficiently close magnetar in any given year is extremely small. The cosmos is not actively trying to end your planet, but the actual capabilities of magnetars are extraordinary, and the empirical study of those capabilities has been one of the more productive areas of modern high-energy astrophysics over the past 50 years. Now, let's begin with the first thing. The magnetic fields of magnetars and what those fields actually mean in physical terms. The magnetic field of a magnetar is the most extreme magnetic field in the known cosmos. To understand what this means, we need to walk carefully through what magnetic fields actually do in physical terms, because the popular intuition about magnetism does not really extend to the regime where magnetars operate. In everyday experience, magnetic fields are gentle. A refrigerator magnet has a field of about 100 Gauss at its surface. A medical magnetic resonance imaging machine produces a field of about 30,000 Gauss, which is strong enough to attract loose metal objects with substantial force and is the reason hospital MRI suites have strict rules about metal objects in the room. The strongest sustained laboratory magnetic fields produced by superconducting magnets at facilities like the National High Magnetic Field Laboratory in Tallahassee reach approximately 1,000,000 Gauss for short pulses. By the end of tonight, you're going to understand that even the strongest laboratory fields are not even close to the regime where magnetars operate. The magnetic field at the surface of a typical neutron star is approximately 1,000,000,000,000 Gauss. Magnetars exceed even this by factors of 100 to 1,000. The most extreme magnetars carry surface magnetic fields of 10 to the 15th Gauss, which is 1 quadrillion times the magnetic field of Earth. At these field strengths, the basic physics changes. The magnetic field becomes strong enough to distort the structure of the vacuum itself through a process called vacuum birefringence. The quantum vacuum, which under ordinary conditions is essentially empty and isotropic, develops different optical properties in different directions when subjected to extreme magnetic fields. Light passing through the field is polarized in specific ways that would not occur under ordinary conditions. The effect has been predicted theoretically since the 1930s and was finally observed indirectly through observations of polarization patterns in light from neutron stars in 2016. The magnetic field at magnetar strength also distorts the structure of atoms themselves. Ordinary atoms, with their electron clouds bound by the electric force, have approximately spherical electron distributions. In the presence of a sufficiently strong magnetic field, the electron clouds are pulled into elongated shapes aligned with the field direction. The atomic structure becomes one-dimensional rather than three-dimensional, with the electrons confined to tight cylinders along the field lines. The chemistry, if any chemistry is even possible under these conditions, would be radically different from anything we observe in normal environments. Pattern interrupt. The chemistry question is, in this sense, somewhat hypothetical. The surface of a magnetar is not a place where ordinary chemistry can operate at all. The temperatures are millions of Kelvin. The gravity is so strong that an object falling from 1 meter above the surface would impact at thousands of kilometers per second. Any matter that might briefly visit the surface would be vaporized, ionized, and accelerated to substantial fractions of the speed of light by the combined effects of gravity, temperature, and magnetic force. The surface conditions are, by every available standard, inhospitable beyond any human framework. The internal magnetic field structure of magnetars is even more extreme than the surface field. Theoretical models suggest that the internal field can reach intensities of 10 to the 16th or even 10 to the 17th Gauss in the deep interior. The internal field provides the energy reservoir that powers the giant flares we will discuss in the second truth. The reservoir is enormous. A single magnetar contains, in its internal magnetic field alone, more energy than the Sun will produce through nuclear fusion across its entire 10-billion-year lifetime. No one expects, on first hearing about magnetic fields, that any object in the cosmos could carry a field a quadrillion times stronger than Earth. No one predicts that the energy stored in such a field could exceed the total fusion energy output of a Sun-like star over its main sequence lifetime. Absolutely no one anticipates the way the magnetic regime of magnetars has become one of the most extreme physical environments that any current theoretical framework attempts to describe. By the end of tonight, you're going to understand that this magnetic environment is what makes everything else about magnetars possible. The giant flares we will discuss next are powered by reconfigurations of this field. The starquakes are caused by the magnetic stress acting on the crust. The fast radio bursts are produced by the magnetic field interactions in the immediate environment of the magnetar. The lethal radius of the giant flares is determined by the energy release made possible by the field. Everything that makes a magnetar what it is depends on the extreme magnetic field. The field is, in this sense, the defining feature. Tonight, we're going to spend a longer pass on the specific history of how magnetars were discovered, because the discovery story is one of the more remarkable in modern high-energy astrophysics and provides essential context for understanding what these objects actually are. The story begins on March 5th of 1979. On that date, a brief and extraordinarily intense pulse of gamma rays struck the Earth from the direction of the Large Magellanic Cloud, the satellite galaxy of the Milky Way, located approximately 170,000 light-years from Earth. The pulse was detected by a network of gamma-ray detectors aboard various spacecraft, including the Soviet Venera missions, the United States Pioneer Venus mission, and various other satellites. The detection was a coordinated international event with the timing of arrival at the various spacecraft, allowing the source location to be triangulated with reasonable precision. The initial gamma-ray pulse lasted only about 1/10 of a second. It was followed by a longer-lasting decay of softer X-ray emission, with the decay lasting approximately 3 minutes. The combined event was unlike anything previously observed. The standard gamma-ray bursts known at the time were typically much longer in duration and showed different spectral evolution patterns. The March 5th event was, by every available standard, a new class of phenomenon. The Soviet astronomer Yevgeny Mazets and his collaborators at the Ioffa Physical Technical Institute in Leningrad were among the first to recognize the significance of the event. Their analysis, published in late 1979, established that the source was located within the supernova remnant N49 in the Large Magellanic Cloud. The identification of the source with a specific supernova remnant suggested that the underlying object was the compact remnant of the original supernova explosion, presumably a neutron star. By the end of tonight, you're going to understand that this initial identification raised more questions than it answered. The neutron star, called SGR 0526-66 in the modern designation, was not behaving like any other neutron star previously observed. The brief, intense gamma-ray bursts were unlike anything that pulsars or other known neutron stars produced. The subsequent X-ray decay was also unusual. The object was clearly a neutron star, but it was a neutron star of a previously unknown type. Pattern interrupt. Over the following decade, additional similar sources were identified. The objects became known collectively as soft gamma repeaters, or SGRs, because they produced repeated bursts of soft gamma rays. A separate class of objects called anomalous X-ray pulsars, or AXPs, was identified through their unusual X-ray properties. The SGRs and AXPs were not immediately recognized as the same type of object, but their properties showed enough similarity that some researchers began to suspect a connection. The theoretical breakthrough came in 1992, with the work of Robert Duncan at the University of Texas at Austin and Christopher Thompson at Princeton University. Duncan and Thompson developed a theoretical framework in which both SGRs and AXPs could be explained as a single class of object, namely neutron stars with extraordinarily strong magnetic fields. They coined the term Magnetar to describe this class. Their proposal suggested that the magnetic field strengths required to explain the observed properties were approximately 10 to the 15th Gauss, far stronger than any other class of known neutron stars. The Duncan and Thomson framework explained several previously puzzling features of the observations. The brief, intense gamma-ray bursts could be explained as energy releases from sudden reconfigurations of the extreme magnetic field. The unusual X-ray properties could be explained as the result of strong magnetic confinement of the surface plasma. The slow rotation periods of the objects, typically several seconds compared to the millisecond periods of ordinary pulsars, could be explained as the result of magnetic braking by the strong field. The framework, in this sense, unified previously disparate observations into a single, coherent picture. By the end of tonight, you're going to understand that the Duncan and Thomson proposal was initially controversial. The required magnetic field strengths were so extreme that some researchers questioned whether such fields could actually exist on neutron stars. The proposal required substantial modifications to the standard models of neutron star formation, with the Magnetar formation channel requiring specific initial conditions involving rapid rotation and strong differential rotation in the proto-neutron star. The skepticism was substantial, but the framework gradually gained acceptance as additional observations confirmed its predictions. Walk with me through some of the specific observational confirmations. The detection of a giant flare from SGR 1900 plus 14 in August of 1998 provided clear evidence that the SGRs could produce events with energies far exceeding those of the smaller bursts that define the class. The detection was made by multiple spacecraft and allowed detailed analysis of the temporal and spectral properties of the event. The properties were consistent with the predictions of the Magnetar framework. The detection of the giant flare from SGR 1806-20 in December of 2004, which we discussed in the second truth, was even more definitive. The flare was so bright that it overwhelmed multiple detectors and was detected through its effects on Earth's ionosphere. The properties of the flare were carefully analyzed, with the results providing direct empirical input to the Magnetar theoretical framework. No one expects, on first encountering the original March 5, 1979 event, that the resolution of the mystery would require essentially a century of follow-up work, both observational and theoretical, to fully establish the Magnetar class as a distinct type of object. No one predicts that the brief gamma-ray pulse from an obscure source in the Large Magellanic Cloud would lead to one of the more dramatic chapters in modern high-energy astrophysics. Absolutely no one anticipates the way the discovery and characterization of magnetars has unfolded across more than 4 decades of careful empirical and theoretical work. The current census of known magnetars includes approximately 30 objects in our own galaxy, plus several additional candidates in nearby galaxies. The objects are detected primarily through their X-ray emission, with occasional radio and infrared detections of specific sources. The total Magnetar population in our galaxy, including objects that have not yet been identified, is estimated at perhaps several hundred, with the lifetime of Magnetar behavior being only about 10,000 years before the magnetic field decays to levels comparable to ordinary neutron stars. Hold this image. Magnetars were discovered through the careful analysis of brief gamma-ray pulses that appeared unlike anything else in the cosmic high-energy sky. The understanding of what these objects actually were emerged over decades of follow-up work. The current empirical and theoretical picture is one of a specific class of extraordinarily magnetized neutron stars, with properties that the broader theoretical community has gradually come to accept as a real feature of the cosmic landscape. By the end of tonight, you're going to understand that this discovery history is part of what makes magnetars so empirically interesting. The objects were not predicted in advance, they were discovered through observations of unusual events. The understanding of their nature required substantial theoretical innovation. The empirical confirmation has come gradually through multiple, independent observations across multiple decades. The story is, in this sense, one of the more remarkable examples of how modern astrophysics actually advances. Hold this image. A small, dense neutron star, about 12 miles across, carrying a magnetic field so strong that no other object in the cosmos can match it. The field is the engine. The field is the reservoir. The field is the source of every extraordinary capability that we will walk through tonight. Magnetars are, in this strict sense, magnetic objects in a way that no other class of celestial body is. The second thing every magnetar can do is release more energy in a fraction of a second than the Sun produces in 250,000 years. Tonight, we're going to walk into the giant flare phenomenon carefully, because the giant flares are the most dramatic empirical demonstration of what magnetars actually are. A giant flare from a magnetar is a sudden release of magnetic energy triggered by a reconfiguration of the magnetic field structure of the star. The reconfiguration happens when the field becomes unstable and snaps into a new configuration, releasing the difference in stored energy between the old configuration and the new one. The release is fast, occurring on timescales of milliseconds to seconds depending on the specific mechanism. The energy emerges primarily as gamma rays, with smaller fractions in X-rays, optical and radio wavelengths. The energy involved is extraordinary. A typical giant flare releases approximately 10 to the 46 ergs of energy. To put this into perspective, the Sun releases approximately 4 times 10 to the 33 ergs of energy per second through nuclear fusion. The total energy output of the Sun over 250,000 years is approximately 10 to the 46 ergs. A magnetar giant flare therefore releases in a fraction of a second an amount of energy equivalent to the entire fusion output of the Sun over 250,000 years. By the end of tonight, you're going to understand why this matters. The energy release is so concentrated in time that the resulting electromagnetic burst is one of the brightest events in the universe at gamma-ray wavelengths. Across cosmic distances, magnetar giant flares can be detected by the gamma-ray detectors operated by various space missions. The Fermi Gamma-Ray Space Telescope, the SWIFT mission, and the older Compton Gamma-Ray Observatory have all detected giant flares from magnetars within our galaxy and from extragalactic sources. The frequency of detection allows us to estimate the cosmic rate of magnetar giant flares, with the rate being substantial but not so high that any specific location in the galaxy is at high risk from any specific magnetar in any specific year. Pattern interrupt. The most powerful giant flare ever observed inside our galaxy occurred on December 27th of 2004. The flare came from a magnetar called SGR 1806-20, located approximately 50,000 light-years from Earth in the constellation Sagittarius. The flare released approximately 10 to the 46 ergs of total energy in about 0.2 of a second. The initial burst, lasting only milliseconds, was so bright at gamma-ray wavelengths that it temporarily overwhelmed the detectors on multiple satellites and saturated the gamma-ray monitoring systems of essentially every active spacecraft. The effects of the December 27th event were measurable across the entire solar system. The gamma-ray burst arrived at Earth and ionized the upper atmosphere, with effects detectable in ionospheric measurements made by ground-based observatories. The burst affected the cosmic ray monitors operated by various space missions. The brightness, measured in gamma rays, briefly exceeded the brightness of the full moon by a substantial margin. The event was, by every reasonable measure, one of the most powerful electromagnetic events ever observed inside our galaxy. The fact that the source was 50,000 light-years away is what saved Earth from any serious consequences. The gamma-ray flux at the top of Earth's atmosphere, while detectable, was not high enough to produce substantial atmospheric chemistry changes. The ionospheric effects, while measurable, returned to normal within hours. The cosmic ray monitor effects faded within days. The event was a remote astronomical curiosity rather than a local disaster. Walk with me through what would have been different if the source had been closer. The gamma-ray flux at any location depends on the energy of the burst divided by the surface area of a sphere of radius equal to the distance to the source. The flux, therefore, falls off as the inverse square of the distance. A magnetar producing the same giant flare at a distance of 1 light-year instead of 50,000 light-years would deliver a gamma-ray flux at Earth that is approximately 2.5 billion times greater than what we actually received in 2004. The flux at 1,000 light-years would be approximately 2,500 times greater than what we received from SGR 1806-20. Even at the much greater distance of 10,000 light-years, the flux would be 25 times what we actually received, which would be enough to produce substantial atmospheric chemistry changes and possibly significant effects on the biosphere. By the end of tonight, you're going to understand that this scaling explains why the lethal radius of a magnetar giant flare extends to such substantial distances. The flux scales with distance squared. The lethal threshold depends on what specific atmospheric and biospheric effects are considered acceptable, but for the most powerful giant flares, the radius at which substantial damage to a planetary biosphere becomes plausible extends to approximately 1,000 light-years and possibly further. The fifth truth tonight will return to this calculation in more detail. The mechanism that produces the giant flares has been worked out in considerable detail. The leading model, developed primarily by Robert Duncan and Christopher Thompson in the 1990s and refined by various researchers since, attributes the flares to sudden reconfigurations of the internal magnetic field structure of the magnetar. The field, twisted and stressed by the rotation and the internal dynamics of the star, periodically reaches configurations that are unstable. The instability triggers a rapid reconnection event in which the field lines snap into new configurations and release the stored energy. The energy release is highly concentrated in time and space. The initial reconnection event occurs in a region of perhaps a few kilometers across, with timescales of milliseconds. The energy is then radiated outward through a complex process involving the interaction of the magnetic field with the surrounding plasma. The outgoing burst is highly directional in the most extreme cases, with the energy concentrated into narrow cones along the magnetic axis. The cone geometry has implications for who actually sees a given giant flare, because a planet outside the cone would receive substantially less radiation than a planet inside it. No one expects, on first thinking about cosmic high-energy events, that a single object only 12 miles across could release more energy in a fraction of a second than an entire star produces over hundreds of thousands of years. No one predicts that the mechanism for such an energy release would involve nothing more exotic than the sudden reconfiguration of a magnetic field. Absolutely no one anticipates the way the giant flares of magnetars have become one of the more dramatic empirical demonstrations of fundamental high-energy physics in the modern era. The cosmic rate of giant flares can be estimated from the observed events. Inside our galaxy, giant flares occur approximately once per several decades. The estimate is based on the observed events, which include the December 27th of 2004 flare from SGR 1806-20, an earlier flare from the same source in 1979, and a flare from SGR 1900 plus 14 in 1998. The events are rare but not unprecedented. Future giant flares are expected, with the timing being random, but the long-term rate being approximately one event per several decades. Pattern interrupt. The implications for Earth depend on which magnetars produce the future flares and on which directions the flares are pointed. A future giant flare from a magnetar at substantial distance similar to SGR 1806-20 would produce measurable effects at Earth, but no serious consequences. A future giant flare from a much closer magnetar, if any such magnetar exists at sufficiently close range, could produce more serious effects. The currently known magnetar population includes no objects at sufficiently close range to produce serious effects from any plausible giant flare. The probability of a previously unknown magnetar producing a serious event at Earth is small, but not strictly zero. Hold this image. Magnetars produce, in a single brief burst, the energy equivalent of 250,000 years of solar fusion output. The bursts are detected across cosmic distances. The bursts within our galaxy have been detected directly. The most powerful event observed to date came from a magnetar 50,000 light-years away and was still detectable through its effects on Earth's atmosphere. The objects are, by every available measurement, the most powerful sustained gamma-ray sources known. By the end of tonight, you're going to understand that this energy release capability is what justifies the second truth. A magnetar is not just a strongly magnetized neutron star. It is an object capable of releasing in seconds what a star releases in hundreds of thousands of years. The cosmic violence involved is extraordinary, and the empirical study of that violence has been one of the more active areas of high-energy astrophysics over the past 3 decades. Before we walk into the third thing, take a slow breath here. The story is about to take a brief turn into a different kind of conversation. Tonight, we're going to spend a careful pass on the December 27th of 2004 giant flare from SGR 1806-20, because the event remains the most powerful electromagnetic phenomenon ever observed within our galaxy, and the empirical details are worth understanding in considerable depth. The source itself, SGR 1806-20, is located approximately 50,000 light-years from Earth in the constellation Sagittarius, near the galactic center. The object is one of the most well-studied magnetars, with extensive observations dating back to the late 1980s, when it was first identified through its bursts of soft gamma rays. The magnetar has a rotation period of approximately 7.5 seconds and a magnetic field strength estimated at approximately 10 to the 15th Gauss. placing it firmly within the Magnetar class. The events leading up to the December 27th flare followed a pattern of increasing activity over several weeks. The source had been producing relatively frequent smaller bursts, with detected events approximately once per several days in the months leading up to the giant flare. The pattern of increasing activity is now recognized as a possible precursor to giant flare events, with similar precursor patterns observed in other magnetar systems before their largest events. By the end of tonight, you're going to understand that the actual flare event began at approximately 21 hours, 30 minutes, 26 seconds Universal Time on December 27th of 2004. The flare consisted of two main components. The initial spike was an extraordinarily bright burst, lasting only milliseconds, with the peak gamma-ray luminosity at the source estimated at approximately 2 times 10 to the 47th ergs per second. The initial spike was followed by a much longer-lasting decay phase with characteristic oscillations at periods of approximately 7.5 seconds, corresponding to the rotation period of the Magnetar pattern interrupt. The peak luminosity of the initial spike was so extreme that it briefly exceeded the luminosity of the entire observable universe at gamma-ray wavelengths. For a fraction of a second, this single object, only 12 miles across and 50,000 light-years from Earth, was emitting more energy per unit time at gamma-ray wavelengths than all the other gamma-ray sources in the visible cosmos combined. The fact is, by every reasonable measure, one of the most extraordinary statements that can be made about any astrophysical phenomenon. The flare was detected by virtually every active gamma-ray detector in space at the time. The detections included observations by the RHSE satellite, the SWIFT mission, the WIND spacecraft, the Mars Odyssey mission orbiting Mars, the Cassini mission orbiting Saturn, and various other facilities. The wide range of spacecraft locations allowed the source to be triangulated with high precision and confirmed the direction to SGR 1806-20. The energy fluence at Earth from the flare was approximately 1 EARG per square centimetre integrated over the duration of the event. This is, in absolute terms, not particularly large compared to other astrophysical fluxes. The same fluence is delivered by the Sun in about 1 second of normal solar activity. But the Magnetar fluence was delivered in only 0.2 of a second, and it consisted entirely of high-energy gamma rays rather than visible light. The biological and atmospheric effects of high-energy gamma rays are very different from those of visible light, with the gamma rays causing ionization and chemistry changes that visible light cannot. The effects on Earth's atmosphere were measurable. The gamma rays interacted with the upper atmosphere and produced ionization that was detected through changes in the propagation properties of low-frequency radio waves. The ionospheric effects lasted approximately 1 hour before the atmosphere recovered to its baseline state. The cosmic ray detectors operated by various spacecraft also recorded perturbations consistent with the gamma-ray pulse and its associated secondary radiation. By the end of tonight, you're going to understand that the analysis of the flare has produced substantial constraints on the underlying physics. The total energy released in the flare has been estimated at approximately 10 to the 46 ergs in the initial spike, with comparable energy released over the longer decay phase. The total energy released over the entire event was approximately 3 times 10 to the 46 ergs, making it the most energetic single event ever observed within our galaxy at any wavelength. The mechanism of the flare has been analyzed in detail. The initial spike is consistent with a sudden reconfiguration of the magnetic field structure of the magnetar, with the field reconnecting in a region of perhaps a few kilometers across and releasing the difference in magnetic energy between the initial and final configurations. The subsequent decay phase is consistent with the cooling of the plasma fireball produced by the reconfiguration, with the rotating geometry of the system producing the characteristic 7.5-second oscillations. The analysis has also produced direct constraints on the internal structure of the magnetar through the seismic oscillations we discussed in the third truth. The starquake-induced oscillations were identified in the high-time resolution X-ray data, with specific frequency features at 28 Hz, 54 Hz, 84 Hz, 155 Hz, and various higher frequencies. The frequencies have been used to constrain the density profile of the magnetar crust and the coupling between the crust and the interior. No one expects, on first encountering the magnetar phenomenon, that a single event from a single object could produce such a wealth of empirical input on so many aspects of high-energy astrophysics. No one predicts that one giant flare would simultaneously constrain magnetar magnetic fields, magnetar crust mechanics, magnetar interior structure, and the broader physics of magnetic reconnection in extreme environments. Absolutely no one anticipates the way the December 27th event has become one of the most empirically productive single astronomical events ever observed. Walk with me through what the event implied for the broader picture of cosmic gamma-ray bursts. Some short-duration gamma-ray bursts detected at extragalactic distances had been suspected of being giant flares from magnetars in other galaxies. The December 27th event provided a direct empirical template for what such events would look like. Subsequent analysis of historical short gamma-ray burst catalogues identified several candidates that may have been extragalactic giant flares from magnetars in nearby galaxies. The identifications are still being investigated, but the connection between galactic giant flares and at least some extragalactic short bursts appears to be real. The implications for the long-term cosmic rate of magnetar giant flares are substantial. If giant flares occur in our galaxy approximately once per several decades, and similar rates apply to other galaxies, then the cosmic rate of giant flares across the observable universe is approximately one event per year. The actual detection of extragalactic giant flares is challenging because of their relatively brief duration and short wavelength emission, but the cosmic rate suggests that some of the unidentified short gamma-ray bursts in the historical record may have been such events. Hold this image. The December 27th of 2004 giant flare from SGR 1806-20 remains, 20 years after the event, one of the most empirically productive astronomical events ever observed. The flare released energy equivalent to 250,000 years of solar fusion output in 0.2 of a second. The flare was detected by every active gamma-ray satellite in the solar system. The flare affected Earth's atmosphere through detectable ionospheric effects. The flare produced detailed empirical input on magnetar internal structure through starquake-induced seismic oscillations. The flare established the empirical template for magnetar giant flares more broadly. By the end of tonight, you're going to understand that this event is, in many ways, the defining empirical demonstration of what magnetars are and what they can do. The 5 truths we are walking through tonight are all illustrated with varying degrees of directness by the specific events of December 27th of 2004. The empirical reality of magnetars rests to a substantial degree on this single extraordinary event and on the careful analysis of its many implications that has been conducted in the 2 decades since. Before we continue, why this channel exists. If you have made it this far into a careful examination of magnetar giant flares, you are not the casual viewer the platform expects. You are the person for whom this channel was built. Long-form astrophysics told at the pace of sleep, with enough technical detail to actually feel the weight of the phenomena rather than just the headline summaries, is not what the algorithm rewards. It is what we make anyway, because we believe the cosmos is more interesting when the questions are developed slowly rather than collapsed into viral fragments. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about cosmic violence and beauty. If you have already subscribed, thank you, truly. If this is your first long-form night with the channel, welcome. The queue contains many more nights like this one. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there. The audio versions are tuned for the same purpose, the same pace, the same care. Now, let us return to the data. The third thing is waiting. The third thing every magnetar can do is crack its own crust through magnetic stress, producing what astronomers call starquakes. Tonight, we're going to walk into the starquake phenomenon carefully, because the starquakes are one of the more direct demonstrations of just how extreme the physical conditions on a magnetar surface actually are. The basic situation is this. A magnetar, like any neutron star, has a solid crust composed primarily of iron and other heavy elements packed to extraordinary densities. The crust extends from the surface inward for approximately 1 kilometer, with the density increasing from roughly the density of ordinary iron at the surface to densities approaching the density of nuclear matter at the base of the crust. Below the crust, the interior of the neutron star is composed of an exotic mixture of neutrons, protons, and possibly more exotic particles in various phases. The crust is held together by the same forces that hold ordinary solid materials together, namely the electromagnetic interactions between charged particles in the crystal lattice. The crust is, by every available measurement, an actual crystalline solid with a specific structure and specific mechanical properties. The strength of the crust, measured as the force per unit area that the material can withstand before fracturing, is extraordinary. Recent calculations suggest that the magnetar crust has a yield strength approximately 10 billion times that of ordinary terrestrial iron. The takeaway is that this strength matters. The magnetic field of a magnetar, with its enormous internal strength, exerts substantial mechanical stress on the crust. The stress arises from the gradients in the magnetic field, which produce forces on the charged particles in the crust through the standard Maxwell stress mechanism. The stress varies across the surface of the magnetar and changes over time as the internal field configuration evolves. Periodically, the stress in some region exceeds the yield strength of the crust, and the material fractures. Pattern interrupt. The fracture is not gentle. The crust of a magnetar is the strongest solid material in the known universe. When it fractures, it releases enormous amounts of energy in the form of seismic waves and electromagnetic emission. The seismic waves propagate through the crust and into the interior, producing complex oscillation patterns that depend on the specific properties of the magnetar. The electromagnetic emission, primarily in X-rays, produces specific observable signatures that can be detected by space-based X-ray observatories. The empirical detection of starquakes has been one of the more remarkable achievements of modern astrophysics. The detection involves identifying specific oscillation features in the X-ray emission following a giant flare or other energetic event. The oscillations correspond to the seismic modes excited in the crust by the fracture event. The frequencies of the oscillations depend on the specific properties of the crust, including its density structure, its composition, and its magnetic field configuration. The measurements allow astronomers to probe the interior of the magnetar in ways that would be impossible without the starquake events. The first definitive detection of starquake-induced seismic oscillations came from the analysis of the December 27th of 2004 giant flare from SGR 1806-20. The Rossi X-ray Timing Explorer satellite operating in low Earth orbit recorded high-time resolution X-ray data during and after the flare. Analysis of the data revealed specific oscillation features at frequencies of approximately 28 Hz, 54 Hz, 84 Hz, and 155 Hz, with various other features at higher frequencies. The oscillations decayed over timescales of minutes to hours, providing a direct probe of the damping mechanisms operating in the magnetar interior. What this leaves us with is that the starquake oscillations provide direct empirical input on the structure of the magnetar interior. The frequencies and amplitudes of the oscillations depend on the specific density profile of the crust, the depth at which the fracture occurred, and the coupling between the crust and the underlying nuclear matter. The data has been used to constrain theoretical models of magnetar structure, with implications for the broader question of what happens to matter under the extreme conditions of neutron star interiors. Walk with me through one specific theoretical implication. The damping rate of the starquake oscillations depends on how efficiently the seismic energy is transferred from the crust to the deeper interior. The transfer depends on the coupling between the crust and the nuclear superfluid that occupies the inner regions of the neutron star. The coupling is mediated by specific quantum mechanical effects involving the rotation of the superfluid. By measuring the damping rate, astronomers can constrain the strength of the crust superfluid coupling and, indirectly, the properties of the superfluid itself. This is, in some sense, a remarkable empirical achievement. The interior of a neutron star is one of the most exotic physical environments in the known cosmos. The matter there exists in phases that cannot be produced in any laboratory on Earth. The conditions are so extreme that the standard frameworks of nuclear and particle physics are pushed to their limits. The starquake observations provide one of the few empirical probes of this regime, with the measurements being possible only because the magnetar crust can store sufficient magnetic stress to produce detectable fracture events. No one expects, on first thinking about astronomical events, that the cracking of a solid surface 12 miles across could be one of the most informative empirical probes of fundamental nuclear physics. No one predicts that the seismology of an object the size of a city, located thousands of light years away, could constrain the structure of nuclear matter under conditions that no laboratory can recreate. Absolutely no one anticipates the way the starquake phenomenon has become one of the more direct empirical windows into the deep interior of neutron stars. The energetics of starquakes provide additional empirical input. A single starquake event can release energy ranging from approximately 10 to the 38 ergs for the smallest detectable events to approximately 10 to the 44 ergs for the most energetic events. The most energetic starquakes are sometimes associated with the giant flares we discussed in the second truth, with the starquake possibly serving as the trigger for the larger magnetic energy release. The exact relationship between starquakes and giant flares is still being worked out, but the connection appears to be direct in at least some cases. The frequency of starquakes is much higher than the frequency of giant flares. Magnetars produce small starquake events approximately once per day or more, with the rate depending on the specific magnetar and on the phase of its magnetic evolution. Most of these smaller events are detectable only through their specific X-ray signatures and do not produce flares bright enough to be detected as discrete events. The cumulative effect of the many small starquakes contributes to the steady X-ray emission that defines magnetars as a specific observational class, pattern interrupt. The starquake phenomenon also provides input on the broader question of how matter behaves under the extreme conditions of neutron star surfaces. The crust of a magnetar is, in this sense, the most extreme solid material in the known universe. The properties of this material are being probed empirically through the seismology of the starquake events. The probes are not perfect, but they are direct, and they constitute one of the more remarkable empirical achievements of modern high-energy astrophysics. The implications for the broader picture of magnetar physics are substantial. The starquakes connect the magnetic field, which we discussed in the first truth, to the giant flares, which we discussed in the second truth. The starquakes are the mechanism by which the magnetic stress in the crust is released, sometimes as small seismic events and sometimes as the trigger for giant flares. The complete picture, taking all three truths together, is one of an object in which extreme magnetic fields produce extreme mechanical stresses, which periodically exceed the strength of even the strongest material in the known universe, producing both the small starquake events that are detectable through specific X-ray signatures and the much larger giant flare events that briefly outshine entire galaxies at gamma-ray wavelengths. Tonight, we're going to walk into the specific structure of the magnetar crust, because the crust is the most extreme solid material in the known cosmos, and its properties are worth understanding in some detail. The crust of a neutron star, including a magnetar, extends from the surface inward for approximately 1 kilometer. The crust is a solid material composed of ions arranged in a crystalline lattice. The composition of the crust varies with depth, with the lightest ions at the surface and progressively heavier ions at greater depths. The lattice is held together by the electromagnetic interactions between the ions and by the degenerate electron gas that pervades the structure. Before we get started, sit with this. The surface composition of the crust depends on the specific history of the magnetar and on the conditions during its formation. For typical magnetars, the surface composition is dominated by iron with smaller fractions of other heavy elements. The surface density is approximately 10 to the 6th grams per cubic centimeter, which is far denser than ordinary terrestrial iron but represents the lowest density region of the crust. What surfaces from this is that the density increases rapidly with depth into the crust. At a depth of approximately 100 meters below the surface, the density reaches approximately 10 to the 11th grams per cubic centimeter. At this density, a significant fraction of the electrons have been forced into the inner shells of the ions through the extreme pressure, in a process called electron capture. The resulting ions are neutron-rich, with substantially more neutrons than the corresponding stable isotopes on Earth. Pattern interrupt. As the depth increases further, the density continues to rise. At depths of approximately several hundred meters, the density reaches the so-called neutron drip density, approximately 4 times 10 to the 11th grams per cubic centimeter. At this density, free neutrons begin to leak out of the ion nuclei and form a separate neutron fluid that coexists with the ionic crystal lattice. The structure becomes a complex composite material with a crystalline lattice of neutron-rich ions embedded in a fluid of free neutrons. The structure, at even greater depths, becomes progressively more exotic. The neutron fluid forms a superfluid state with specific quantum mechanical properties that have implications for the dynamics of the magnetar. The ionic lattice continues to be present, but with progressively more neutron-rich ions. At the base of the crust, approximately 1 kilometer below the surface, the density reaches approximately 10 to the 14th grams per cubic centimeter, which is approaching the density of an atomic nucleus itself. Below this depth, the crust ends and the interior of the neutron star begins, with the interior consisting of a homogeneous nuclear fluid rather than a structured, crystalline material. What emerges from this is that the mechanical properties of the crust are dominated by the strength of the ionic lattice and the electrostatic interactions between the ions. The yield strength of the crust, the maximum stress it can withstand before fracturing, has been calculated theoretically through molecular dynamics simulations. The recent calculations by Charles Horowitz at Indiana University and Kai Kadau at the Los Alamos National Laboratory suggest that the yield strength is approximately 10 billion times that of ordinary terrestrial iron. The crust of a magnetar is, by this calculation, the strongest solid material known. The mechanism of crust fracture under the extreme magnetic stresses of a magnetar has also been worked out theoretically. The magnetic field exerts forces on the charged particles in the crust through the standard Maxwell stress mechanism. The forces vary across the surface and within the crust, producing internal stress patterns that depend on the specific field configuration. When the stress exceeds the yield strength in some region, the crust fractures and releases energy in the form of seismic waves and electromagnetic emission. The detailed dynamics of crust fracture under these conditions has been studied through numerical simulations. The simulations suggest that the fractures can be sudden and catastrophic, with the entire stressed region releasing its energy on timescales of milliseconds. The released energy is partitioned between several different channels. Some of the energy goes into seismic waves that propagate through the crust and into the interior. Some of the energy goes into electromagnetic emission, primarily in X-rays. Some of the energy goes into the local heating of the fracture region, with temperatures briefly reaching values that would otherwise require active fusion reactions. No one expects, on first thinking about extreme materials, that the strongest solid in the cosmos would be the surface layer of an exotic stellar remnant, rather than something synthesized in a terrestrial laboratory. No one predicts that the yield strength of magnetar crust would exceed ordinary terrestrial materials by 10 orders of magnitude. Absolutely no one anticipates the way the theoretical and observational study of magnetar crusts has become one of the more interesting areas of extreme materials research. The connection between the crust fractures and the magnetar giant flares has been the subject of substantial research. The leading model suggests that the giant flares are triggered by particularly large crust fractures, with the fracture releasing magnetic stress. that then propagates outward through the magnetosphere and produces the gamma-ray burst. The detailed mechanism is complex, involving the coupling between the mechanical fracture and the magnetic reconnection that produces the gamma-ray emission. The starquake-induced seismic oscillations we discussed in the main text provide direct empirical input on the crust properties. The frequencies of the oscillations depend on the elastic properties of the crust, the density structure, and the boundary conditions at the surface and at the base of the crust. By analyzing the observed oscillation frequencies, astronomers can constrain these properties and indirectly probe the structure of the Magnetar interior. Walk with me through one specific result. The analysis of the seismic oscillations following the December 27th giant flare from SGR 1806-20 allowed astronomers to estimate the mass and radius of the underlying magnetar. The estimates are not as precise as those from other neutron star observations, but they provide independent input to the broader question of neutron star structure. The values derived from the seismic analysis are consistent with the values derived from other observations, lending confidence to both approaches. The point worth taking away is that the crust of a magnetar is, in this sense, both an extraordinary material and an empirically accessible probe of fundamental physics. The crust is the strongest solid known. The crust can fracture under the extreme magnetic stresses produced by the magnetar's field. The fractures produce observable signatures that constrain the crust properties. The complete picture is one of an extraordinary material whose extreme behavior is, despite its inaccessibility, becoming progressively better characterized through careful observational and theoretical work. Hold this image. A magnetar is, in this respect, a uniquely violent object. The cosmic violence is mediated by the magnetic field, manifested through the mechanical stress, and observed through both the routine starquake events and the rare giant flares. The empirical signatures of these processes have been one of the more productive areas of modern high-energy astrophysics, with the observations providing direct input on physics that cannot be tested in any other way. What follows from this is that the third truth ties the first two truths together. The magnetic field is the engine. The giant flares are the most dramatic energy releases. The starquakes are the mechanism that bridges them. The complete picture is one of an object whose every observable behavior is in some way an expression of the extreme magnetic conditions that define what a magnetar is. The fourth thing every magnetar can do is produce fast radio bursts, the brief and powerful flashes of radio emission that have been one of the great empirical puzzles of modern astronomy. Tonight, we're going to walk into the connection between magnetars and fast radio bursts carefully, because the connection was established in 2020 after a decade of speculation, and the implications for understanding both magnetars and the broader cosmic radio sky are substantial. Fast radio bursts, called FRBs in the technical literature, were discovered in 2007 through the analysis of archival data from the Parkes Radio Telescope in Australia. The first detected burst, called the Lorimer burst after the astronomer Duncan Lorimer, who identified it, was a brief and intense pulse of radio emission lasting only about 5 milliseconds. The properties of the burst were striking. The dispersion measure of the signal, which describes how much the burst's arrival time depends on radio frequency due to interactions with intervening ionized gas, was much higher than any galactic source could plausibly produce. The implication was that the burst came from somewhere outside our galaxy, at a substantial cosmic distance. For the next decade, the field of FRB astronomy struggled to understand what these bursts actually were. Hundreds of additional bursts were detected, primarily by the Parkes telescope, and subsequently by other facilities including the KIME telescope in Canada and the ASCAP array in Australia. The bursts varied in their properties. Some were one-time events that never repeated. Others were observed to repeat from the same location on the sky, sometimes hundreds of times. The host galaxies of some bursts were identified, allowing the distances to be measured directly. The bursts were, in essentially every confirmed case, located at substantial cosmic distances, with the most distant FRBs originating from galaxies billions of light-years from Earth. What this means is that the source mechanism remained unclear for the better part of a decade. Various proposals were advanced. Some involved magnetars, some involved colliding neutron stars, some involved cosmic string interactions, evaporating primordial black holes, and various other exotic mechanisms. The proposed magnetar mechanism, developed by various theorists over the years, suggested that giant flares or other magnetic events on magnetars could produce coherent radio emission detectable across cosmic distances. The mechanism was theoretically viable but had not been directly confirmed. Pattern interrupt. The definitive confirmation came on April 28th of 2020. On that date, two independent telescopes, the KIME telescope in British Columbia and the STARE-2 array of radio receivers in the United States, simultaneously detected a fast radio burst. The burst was much brighter and much closer than any previous FRB detection. The source was localized to a known magnetar in our own galaxy, called SGR 1935 plus 2154, located approximately 30,000 light-years from Earth in the constellation Vulpecula. The detection was a definitive empirical confirmation that at least some fast radio bursts come from magnetars. The burst, while much less luminous than the typical extragalactic FRBs, had all the characteristic properties of an FRB: the dispersion measure, the duration, the spectral structure, and the polarization properties were all consistent with the FRB class. The only difference was the brightness, which was much higher at Earth because the source was so much closer than the typical extragalactic source. What this picture tells us is that what this means for the broader picture of cosmic radio astronomy. The detection establishes that magnetars are at least one source of fast radio bursts. Whether magnetars are the only source remains an open question. Other classes of FRBs, particularly the very brightest ones detected at extragalactic distances, may involve different mechanisms or may involve magnetars in more extreme magnetic environments than the typical galactic magnetar. The question is being actively investigated. The mechanism by which magnetars produce fast radio bursts has been the subject of substantial theoretical work. Several specific scenarios have been advanced. One scenario involves coherent emission from the magnetosphere of the magnetar, with the radio burst being produced by the rapid acceleration of charged particles in the field. Another scenario involves emission from a shock front, produced when the magnetar's flare interacts with the surrounding interstellar medium. A third scenario involves more exotic processes, including quantum mechanical effects, in the extreme magnetic environment near the magnetar. The current data does not yet definitively distinguish between these scenarios. The empirical work continues, with both the radio detections and the multi-wavelength follow-up observations providing input on which mechanism actually operates. The next several years of FRB observations, combined with the continuing study of galactic magnetars, will likely substantially advance our understanding of how the bursts are produced. No one expects, on first thinking about cosmic radio emission, that the brief and powerful bursts detected from cosmic distances could be coming from objects only 12 miles across. No one predicts that the connection between magnetars and fast radio bursts would be definitively established through the simultaneous detection of a burst from a galactic magnetar by two independent radio facilities. Absolutely no one anticipates the way the FRB mystery has, after a decade of speculation, finally begun to yield to direct empirical observation. Walk with me through the broader implications. Fast radio bursts have become one of the most productive observational tools in modern cosmology. The dispersion measure of FRBs encodes information about the intervening intergalactic medium, including the density of ionized gas, along the line of sight. By measuring the dispersion measures of many FRBs at various distances, cosmologists can map the baryonic content of the cosmos at cosmological scales. The mapping has produced specific results, including the recent confirmation of the so-called missing baryon problem, in which the observed baryonic content of the cosmos matches the predictions of Big Bang nucleosynthesis once the FRB detected intergalactic medium is properly accounted for. The FRBs are, in this sense, more than just astronomical curiosities. They are tools that provide direct, empirical input on fundamental cosmological questions. The connection to magnetars means that magnetars, despite being individually exotic objects, contribute to one of the more productive observational programs in modern cosmology. The cosmic rate of FRBs is enormous. Recent CHIME observations have detected thousands of FRBs, and the inferred cosmic rate is approximately 1,000 bursts per day across the observable sky. The vast majority of these bursts come from distant galaxies and require sensitive instruments to detect. The brightness distribution and the host galaxy properties of the bursts are being mapped through ongoing observations, with the goal of understanding what fraction of bursts come from magnetars versus other possible sources. Pattern interrupt. The implications for magnetar physics are substantial. If the typical FRB comes from a magnetar producing emission similar to the April 2020 event from SGR 1935 plus 2154, then the magnetar emission must be more luminous in some cases than in others. The variation may reflect different magnetic field configurations, different ages of the magnetars, or different specific events. Understanding the variation is one of the active questions in current FRB research. The empirical picture, taking all the evidence together, suggests that magnetars are an important component of the FRB population, but may not be the only contributor. Some FRBs may come from more exotic mechanisms or from magnetars in more extreme environments than the typical galactic source. The mix of source populations is being mapped through ongoing observations, with the next several years expected to produce substantial clarification. Tonight, we're going to walk through the specific details of the April 28th of 2020 event from SGR 1935 plus 2154. Because the event was the first definitive empirical connection between magnetars and fast radio bursts, and the details deserve careful attention, the source itself, SGR 1935 plus 2154, was identified as a magnetar in 2014 following the detection of a series of soft gamma-ray bursts from its location. The source is located approximately 30,000 light-years from Earth in the constellation Vulpecula, far from the galactic center but well within the disk of the Milky Way. The Magnetar has a rotation period of approximately 3¼ seconds and a magnetic field strength estimated at approximately 2 times 10 to the 14th Gauss, placing it firmly within the Magnetar class, but at the lower end of the magnetic field distribution for known magnetars. The events leading up to the April 28th burst followed a pattern of increasing activity, similar to the precursor pattern observed before the December 2004 giant flare from SGR 1806-20. SGR 1935 plus 2 154 had been producing relatively frequent bursts of soft gamma rays in the weeks before the radio detection, indicating that the Magnetar was in an active phase. The activity was being monitored by multiple X-ray observatories, including the SWIFT satellite and the NICER instrument on the International Space Station. Notice that the radio detection on April the 28th came from 2 independent instruments. The first was the CHIME telescope, the Canadian Hydrogen Intensity Mapping Experiment located at the Dominion Radio Astrophysical Observatory in British Columbia. CHIME is a wide-field radio telescope optimized for detecting brief transient radio signals across a substantial portion of the sky. The second instrument was the STARE-2 array, the Survey for Transient Astronomical Radio Emission, consisting of 3 small radio receivers located at separate sites in California, Utah, and Washington State. STARE-2 was specifically designed to detect bright radio bursts that would saturate or be missed by more sensitive but narrower field instruments. Both instruments detected a single brief radio pulse on April the 28th at approximately 14 hours, 34 minutes, 24 seconds, universal time. The pulse lasted approximately 1 millisecond. The dispersion measure of the pulse was consistent with the previously known dispersion measure of SGR 1935 plus 2 154, which had been established through observations of the Magnetar's normal X-ray emission. The pulse properties were characteristic of the fast radio burst class, with the brief duration, the substantial brightness, and the specific spectral structure, all matching the established FRB definition. Pattern interrupt. The simultaneous detection by 2 independent radio facilities combined with the simultaneous detection of an associated X-ray burst by the SWIFT satellite provided unambiguous evidence that the radio pulse came from SGR 1935 plus 2 154. The detection was a definitive empirical confirmation that magnetars can produce fast radio bursts. The implications for the broader field of FRB astronomy were substantial and immediate. The properties of the April 28th burst placed it at the boundary between fast radio bursts and the more typical radio activity observed from galactic radio sources. The total energy released in the radio band was approximately 10 to the 35th ergs, which is much smaller than the energies of typical extragalactic FRBs, which can reach 10 to the 40th ergs or more. The April 28th event was, in this sense, a relatively low-energy FRB by extragalactic standards. The fact that it was detectable at all was due primarily to the relatively close distance of the source compared to typical extragalactic FRBs. The simultaneous X-ray detection added important context. The swift detection of an X-ray burst at the same time as the radio pulse established that the Magnetar was producing energy releases across multiple wavelength bands simultaneously, with the radio emission being just one component of a multi-wavelength event. The relative intensities of the radio and X-ray emission provided constraints on the underlying emission mechanism, with implications for which of the various theoretical models for FRB production might apply. What becomes clear is that the April 28th event did not by itself resolve the question of whether all FRBs come from magnetars or whether other source classes also contribute. The April event was, in some ways, simpler than typical extragalactic FRBs. The typical extragalactic FRBs show more complex temporal and spectral structure than the April event, with some FRBs exhibiting repeated bursts from the same source separated by minutes to hours. The relationship between the simpler galactic event and the more complex extragalactic events remains an active area of investigation. The subsequent observations of SGR 1935 plus 2 154 have detected additional radio emission, with several follow-up bursts being detected over the months following April the 28th. The follow-up bursts have been generally similar in properties to the original event, with some variation in brightness and duration. The pattern is consistent with the source being a recurring FRB source, with the Magnetar producing radio bursts during specific phases of its activity. No one expects, on first thinking about astronomical events, that a single detection from a single galactic source could so definitively resolve a decade-long puzzle about the nature of cosmic radio bursts. No one predicts that the simultaneous detection by two independent facilities of a brief radio pulse from a known galactic magnetar would provide the empirical breakthrough that the broader field had been seeking. Absolutely no one anticipates the way the April 28th event has reshaped the field of FRB astronomy in such a fundamental way. Walk with me through the broader implications. The detection establishes that magnetars are at least one source of FRBs. The cosmic rate of magnetars combined with the rate of magnetar activity can be used to estimate the contribution of magnetars to the total FRB population. The current estimates suggest that magnetars can plausibly account for a substantial fraction of the observed FRB population, possibly the majority. The question of whether other source classes also contribute remains open, but the Magnetar contribution has been empirically established. The implications for the broader use of FRBs as cosmological tools are also substantial. Fast radio bursts have been used in recent years to study the intervening intergalactic medium through their dispersion measures. The connection to magnetars means that the FRB sources are sufficiently common and sufficiently well distributed across cosmic distances that they can serve as effective probes of the cosmic baryonic content. The recent results on the missing baryon problem, in which the observed FRB dispersion measures match the predictions of Big Bang nucleosynthesis for the total cosmic baryon content, depend on the FRBs being produced by sources that are sufficiently common to allow systematic study. Hold this image. The April 28th of 2020 event from SGR 1935 plus 2 154 established the empirical connection between magnetars and fast radio bursts. The event was detected simultaneously by two independent radio facilities and by the Swift X-ray Observatory. The detection was definitive. The implications for FRB astronomy were immediate and substantial. The event is, in this sense, one of the most consequential single observations in recent radio astronomy. Step back, and you can see that the connection between magnetars and FRBs is part of what makes magnetars so empirically important. The objects, despite their individual rarity, contribute to one of the most productive observational programs in modern cosmology. The fourth truth, that magnetars can produce fast radio bursts, is therefore not just a curiosity about magnetar physics. It is a connection to one of the more active areas of modern astrophysical research. Hold this image. Magnetars, despite their individual rarity, are contributing to one of the most productive observational programs in modern cosmology. The fast radio bursts they produce travel across cosmic distances, carrying information about the intervening cosmos and about the magnetars themselves. The empirical detection of a galactic magnetar producing an FRB-like event has been one of the more important results in modern radio astronomy, definitively connecting two previously separate fields of study. The takeaway is that the fourth truth is, in this sense, both about magnetars specifically and about the broader picture of cosmic radio astronomy. Magnetars do something that no other class of object is known to do in the same way. They produce brief bursts of coherent radio emission detectable across cosmic distances. The bursts have become a productive observational tool for cosmology. The connection between the individual magnetars and the cosmic bursts is one of the more remarkable empirical achievements in modern astrophysics. The fifth thing every magnetar can do is, in some ways, the most consequential. A magnetar at a distance of 1,000 light-years could, under specific circumstances, end the habitability of a planet around a completely innocent star. Tonight, we're going to walk through this carefully because the lethal radius of a magnetar giant flare is a real physical quantity that can be calculated from first principles and validated against observed events. The basic mechanism is straightforward. A magnetar giant flare delivers a brief but intense burst of gamma rays to whatever environment is in the path of the burst. The gamma rays interact with the upper atmosphere of any planet in the path, producing several specific effects. The first effect is direct ionization of the atmosphere, with the ionized particles producing secondary radiation and altering the chemistry of the atmospheric layers. The second effect is the destruction of the ozone layer through specific photochemical reactions involving the ionized species. The third effect is the production of nitrogen oxides, which deplete the ozone over longer time scales and produce additional effects on the atmospheric chemistry. The fourth effect is the surface ultraviolet flux, which increases substantially after the ozone destruction and can cause direct biological damage on the planet's surface. The lethal radius depends on which specific effects are considered acceptable. The complete sterilization of a planet, in the sense of killing all surface life, requires very high gamma-ray flux and is plausible only for very close magnetar sources. The mass extinction of biological species with significant loss of biodiversity but survival of some life is plausible at greater distances. The substantial atmospheric chemistry effects, with measurable changes to atmospheric composition and possibly to the climate, are plausible at even greater distances. What this leaves us with is that the specific calculations that go into estimating these lethal radii. The fundamental quantity is the gamma-ray fluence at the top of the atmosphere of the receiving planet. The fluence depends on the total energy of the giant flare divided by the surface area of a sphere of radius equal to the distance to the source. For the most powerful possible giant flares, with total energies approaching 10 to the 47 ergs, the fluence at a distance of 1,000 light-years is approximately 100 kilojoules per square meter at the top of the atmosphere. Catch the texture of this. To put this fluence into context, the typical solar X-ray flux during a major solar flare event is approximately 1 millijoule per square meter at Earth. The most powerful solar proton events deliver perhaps a few hundred millijoules per square meter to the top of the atmosphere. A magnetar giant flare from 1,000 light-years would deliver approximately 1,000,000 times the energy of the largest observed solar event. The biological and atmospheric consequences would be correspondingly more severe. The specific consequences for a planetary biosphere have been calculated in detail by various researchers, including Adrian Malott at the University of Kansas and Brian Thomas at Washburn University, who have studied the atmospheric and biological effects of various types of cosmic radiation events. Their analyses, applied to Magnetar giant flares, suggest that a planet at 1,000 light-years from a maximally energetic Magnetar giant flare would experience substantial atmospheric chemistry changes. The ozone layer would be substantially depleted, with depletion levels of 50% or more lasting for years to decades. The surface ultraviolet flux would increase by factors of 2 to 10, depending on the wavelength and the atmospheric depth. No one expects this in the popular discussion, but the biological consequences would include direct damage to surface-dwelling organisms, particularly those that rely on ozone protection from ultraviolet, and indirect consequences through atmospheric chemistry effects on the food chain. What surfaces from this is that this is not quite complete sterilization. The biological effects are severe, but not necessarily total. Microbes living below the surface in oceans or under sufficient cover would likely survive the radiation event itself. Many species, particularly those well adapted to high ultraviolet environments, would also survive. The biosphere would not be destroyed entirely, but it would be substantially damaged, with many surface-dwelling species likely facing extinction and with the recovery taking thousands to millions of years. For closer magnetars, the consequences scale rapidly, with decreasing distance. At 100 light-years, the fluence increases by a factor of 100. The ozone depletion would be essentially complete. The surface ultraviolet flux would be high enough to directly sterilize exposed surfaces. The atmospheric chemistry effects would be much more severe and long-lasting. At 10 light-years, the fluence increases by another factor of 100, with consequences that begin to approach complete sterilization of the surface biosphere. No one predicts this when first thinking about cosmic threats. The fortunate fact is that no known magnetar is at a distance of 1,000 light-years or less from Earth. The closest known magnetar, 1E1048.1 -5937, is at approximately 9,000 light-years. At this distance, even the most powerful possible giant flare from this object would deliver a fluence at Earth approximately 80 times lower than the lethal level we have been discussing. The atmospheric effects would be measurable, but the biological consequences would be modest. The probability of a previously unknown magnetar lying within 1,000 light-years of Earth is small, but not strictly zero. The known magnetar population includes only about 30 objects, and the cosmic magnetar census is far from complete. Some fraction of all magnetars in our cosmic neighborhood may simply not have been identified yet. The probability of a previously unknown magnetar producing a giant flare directly at Earth in any given year is, by every available calculation, very low. But the probability is not zero, and the consequences if such an event occurred would be substantial. No one expects, on first thinking about astronomical threats, that the most extreme cosmic objects could pose meaningful threats to planetary biospheres from substantial distances. No one predicts that the lethal radius of any single cosmic event could extend to 1,000 light-years. Absolutely no one anticipates the way the Magnetar giant flare phenomenon has, despite its rarity, become a measurable component of the broader picture of cosmic threats to planetary habitability. Walk with me through the implications for Earth's history, Over the past few billion years, our galaxy has hosted thousands of magnetars across many generations. The probability that one of those magnetars produced a giant flare directly at Earth at some point in Earth's history is, while not certain, not negligible either. Some researchers have proposed that specific extinction events in Earth's history may have been triggered by such cosmic radiation events, with the late Ordovician extinction event of approximately 440 million years ago being one of the candidates. The connection has not been definitively established, but the empirical and theoretical work continues. The implications for other planetary biospheres across cosmic history are also substantial. Many planets across the cosmos must have been in the lethal radius of magnetar giant flares at various points in their histories. Some of those planets may have had biospheres at the time of the events. The consequences for those biospheres would have been severe. The cosmic graveyard of worlds whose biospheres were ended by magnetar events is, by simple statistics, substantial. The empirical detection of past magnetar events affecting Earth is, by every available indication, difficult. The atmospheric chemistry changes from a single brief event would, over geological timescales, be hard to distinguish from other atmospheric perturbations. The biological signatures, if any, would be similarly hard to identify. The work continues with various researchers looking for specific isotope signatures or other markers that might indicate ancient cosmic radiation events. The results so far have been suggestive but not definitive. Sit with this. The broader picture is one of a cosmos in which extreme objects, despite their rarity, can produce substantial consequences across substantial distances. Magnetars are one of the more extreme examples. The cosmic violence they produce, while individual events are rare, has been a feature of the cosmic landscape across the entire history of the universe. The implications for the long-term habitability of any specific planet, including Earth, are real but not catastrophic. The probability of any specific lethal event affecting any specific planet in any specific time window is small. The cumulative probability across geological time scales is not negligible. Tonight, we're going to spend a careful pass on the specific calculations behind the lethal radius for magnetar giant flares because the calculations involve several distinct physical effects, and the details deserve careful examination. The lethal radius depends on what specific consequences are considered acceptable. Different definitions of lethality produce different numerical values for the radius. The complete sterilization of a planetary surface requires very high gamma-ray flux and is plausible only for relatively close sources. Mass extinction of biological species with significant biodiversity loss, but survival of some life is plausible at greater distances. Substantial atmospheric chemistry changes with measurable but recoverable consequences are plausible at even greater distances. The fundamental quantity in the calculations is the gamma-ray fluence at the top of the atmosphere of the receiving planet. The fluence depends on the total energy released by the giant flare divided by the surface area of a sphere of radius equal to the distance from the source. For a flare releasing 10 to the 46 ergs of total energy, the fluence at 1,000 light-years is approximately 100 kilojoules per square meter at the top of the atmosphere. What emerges from this is that how this fluence compares to other relevant physical scales. The biologically lethal radiation dose for most surface organisms is approximately 10 sieverts of ionizing radiation. The relationship between gamma-ray fluence and biological dose depends on the specific gamma-ray spectrum and the depth at which the dose is being calculated. For typical magnetar flare spectra, a fluence of 100 kilojoules per square meter at the top of the atmosphere corresponds to a surface dose of approximately 1 to 10 sieverts in the absence of substantial atmospheric attenuation. Quiet pause. The atmospheric attenuation is critical. A planet with a substantial atmosphere similar to Earth's will attenuate the gamma rays significantly through interactions with atmospheric atoms. The attenuation reduces the surface gamma ray flux by factors of approximately 100 to 1000, depending on the atmospheric column density and the gamma ray spectrum. The direct surface gamma ray dose from a magnetar flare at 1000 light-years would therefore be approximately 10 to 100 millisieverts, which is not directly lethal, but is far above ordinary background levels. The primary lethal mechanism is therefore not the direct gamma ray dose, but the secondary effects on the atmosphere and biosphere. The most important secondary effect is the destruction of the ozone layer. The ozone layer absorbs ultraviolet radiation that would otherwise reach the surface. When the ozone is destroyed by the gamma ray pulse, the surface ultraviolet flux increases substantially, with consequences for surface organisms that depend on ozone protection. The destruction of the ozone layer proceeds through specific photochemical reactions. The gamma rays ionize molecules in the upper atmosphere, producing free oxygen atoms and nitrogen atoms. The free atoms react with ozone molecules through specific reactions that destroy ozone faster than it can be replenished through normal atmospheric processes. The destruction of nitrogen oxides produces a longer-lasting chemical state that continues to deplete ozone for years after the original event. The atmospheric chemistry calculations have been carried out in detail by various researchers. Adrian Melott at the University of Kansas, Brian Thomas at Washburn University, and Charles Jackman at NASA Goddard have published extensive analyses of the atmospheric consequences of various types of cosmic radiation events, including supernova explosions, gamma-ray bursts, and magnetar giant flares. The analyses use detailed atmospheric chemistry models to calculate the depletion of ozone, the production of nitrogen oxides, and the subsequent surface ultraviolet flux changes. The point worth taking away is that the specific results. For a magnetar giant flare at 1000 light-years, the ozone depletion is approximately 50% at the peak, with recovery taking approximately a decade. The surface ultraviolet flux increases by factors of 2 to 10, depending on the wavelength and the latitude. The biological consequences include increased mutation rates for surface organisms, damage to photosynthetic systems in shallow water ecosystems, and possibly significant biodiversity loss for the most ultraviolet sensitive species. The biological consequences are not necessarily complete sterilization. Microbes living below the surface in deep oceans or under significant cover would generally survive the event itself. Many species adapted to high ultraviolet environments, including some bacteria, fungi, and lichens, would also survive. The biosphere would experience substantial damage but not total destruction. The recovery in terms of biodiversity would take thousands to millions of years for the most affected species. For closer magnetars, the consequences scale rapidly with decreasing distance. At 100 light-years, the fluence increases by a factor of 100. The ozone depletion would be essentially complete. The surface ultraviolet flux would be high enough to directly damage exposed organisms within minutes of the event. The atmospheric chemistry would be substantially perturbed for centuries. At 10 light-years, the fluence increases by another factor of 100, with consequences approaching the complete sterilization of the surface biosphere. No one predicts, on first encountering the Magnetar phenomenon, that the lethal radius for a single brief astronomical event could extend to 1,000 light-years. No one expects that the secondary atmospheric chemistry effects could be more important than the direct gamma-ray dose. Absolutely no one anticipates the way the calculations have established magnetars as one of the more substantial astronomical threats to planetary habitability across cosmic distances. Walk with me through what this implies for Earth's past. Over the past 4 billion years, our galaxy has hosted approximately 100,000 magnetars across many generations. The total number of giant flares produced by these magnetars is therefore approximately several billion. The fraction of those flares that occurred within 1,000 light-years of Earth at the time of the flare is, by simple geometric considerations, small but not zero. The probability that at least one such event has affected Earth's biosphere over the past 4 billion years is, by various calculations, approximately 10 to 50%. The empirical search for evidence of such events in Earth's geological record has been an active area of research. Specific isotope signatures, including elevated levels of certain cosmogenic isotopes in geological samples of particular ages, might indicate ancient cosmic radiation events. The most studied case involves the late Ordovician extinction event of approximately 440 million years ago, which has been hypothesized by some researchers to have been triggered or contributed to by a nearby cosmic radiation event. The evidence is suggestive but not definitive. The implications for other planetary biospheres across the cosmos are also substantial. Many planets across cosmic history must have been within the lethal radius of magnetar giant flares at various points. Some of those planets must have hosted biospheres at the time of the events. The total number of planetary biospheres affected by magnetar events across cosmic history is, by simple statistical considerations, large. The cosmic graveyard of biospheres ended or damaged by magnetar events is one of the more concrete examples of how cosmic violence has shaped the broader picture of cosmic life. Hold this image. The lethal radius of a magnetar giant flare is a real, physical quantity that can be calculated from first principles and validated against observed events. For the most powerful possible giant flares, the lethal radius extends to approximately 1,000 light-years and possibly further. The mechanism involves not the direct gamma-ray dose but the secondary effects on atmospheric chemistry and the resulting changes to the surface ultraviolet environment. The empirical and theoretical work continues, with substantial implications for understanding cosmic threats to planetary habitability. What follows from this is that the fifth truth is, in this sense, one of the more consequential single results in modern astrobiology. The cosmos contains objects capable of substantially affecting planetary biospheres at substantial distances. The cosmos is not actively trying to end any specific biosphere, but the cumulative probability of substantial events over cosmic time is not negligible. The implications for the long-term habitability of any specific planet, including Earth, are part of the broader picture of how cosmic conditions actually constrain the possibilities for life. Hold this image. Magnetars are extreme objects with extreme capabilities. The fifth truth, that they can end planetary habitability from 1,000 light-years away, is the most consequential of the 5 truths we have walked through tonight. The mechanism is well understood. The energies are extraordinary. The empirical observations support the theoretical calculations. The cosmic graveyard of worlds whose biospheres were affected by Magnetar events is, by simple statistics, substantial. The cosmos that contains you is, in this respect, more dangerous than the standard impression of a stable cosmic backdrop allows. What this means is that the five truths together constitute a complete picture of what magnetars are and what they can do. The magnetic field is the engine. The giant flares are the energy releases. The starquakes are the mechanism. The fast radio bursts are the cosmic scale signatures. The planet-ending capability is the consequence. The complete picture is one of an object that combines extreme physical properties in ways that no other class of cosmic body can match. Tonight, we're going to spend a careful pass on what magnetars imply for the broader picture of cosmic violence, because the magnetar phenomenon sits within a larger category of extreme cosmic events that have shaped the broader history of cosmic structure and habitability. Before we get started, sit with the basic landscape. The cosmos contains a hierarchy of extreme objects, with each level of extremeness producing characteristic types of cosmic violence. Ordinary stars produce supernovae at the ends of their lives, releasing approximately 10 to the 44 ergs of energy over weeks. Neutron stars in binary systems produce X-ray bursts and pulsar wind nebulae. Black holes produce relativistic jets when they accrete matter at high rates. Active galactic nuclei produce sustained luminosities exceeding the total light output of their host galaxies. Gamma-ray bursts, the most luminous transient events in the cosmos, can briefly outshine entire galaxies. Magnetars sit within this hierarchy as one of the most extreme classes of objects in terms of magnetic field strength, and as one of the more productive classes in terms of brief energy releases. The Magnetar giant flares, with their 10 to the 46 erg releases in fractions of a second, are among the most powerful brief events ever observed within our galaxy. Only the gamma-ray bursts from collapsing massive stars or from merging neutron stars exceed the magnetar flares in raw energy release, and even those typically occur on longer timescales than the magnetar events. What this picture tells us is that the cosmic rate of various types of extreme events shapes the broader picture of planetary habitability. Supernovae occur in our galaxy approximately once per 50 years, producing electromagnetic effects detectable across substantial distances. Magnetar giant flares occur approximately once per several decades. Long gamma-ray bursts within our galaxy may occur approximately once per several million years, but their effects are much more directional and intense when they do occur. The various types of events together produce a steady background of cosmic violence at levels that, over geological timescales, has substantial implications for the long-term habitability of any specific planetary biosphere. Notice the shift. The implications for Earth specifically have been considered in some detail. Over the past 4.5 billion years since Earth's formation, the cumulative number of cosmic events that could potentially have affected the biosphere is substantial. Some of those events have been documented through specific geological signatures. The iron 60 deposits in deep ocean sediments from approximately 2.5 million years ago and approximately 7 million years ago, which we have discussed in other contexts, are the most definitive examples. The events did not sterilize Earth, but they did produce measurable atmospheric and possibly biological effects. The implications for other planets across the cosmos are similarly substantial. Most planets, over their lifetimes, will experience some number of significant cosmic radiation events. The number depends on the specific location of the planet within its galaxy, the local stellar density, the cosmic rate of various event types, and the duration over which the planet has been potentially habitable. Some planets will be lucky and experience few significant events. Others will be unlucky and experience many. The variation across cosmic planetary populations contributes to the broader picture of how cosmic conditions actually constrain the possibilities for life. The galactic location of any specific planet also matters substantially. Planets located in dense stellar regions near the galactic center experience higher rates of cosmic radiation events than planets located in the quieter outer disk. The galactic habitable zone, the region of the galaxy in which the rate of cosmic radiation events is low enough to permit long-term biological evolution, is a real geographic feature. Earth's location, approximately 26,000 light-years from the galactic center, in a relatively quiet region between major spiral arms, has been favorable for the long-term continuity of the biosphere. Notice that this is part of why Earth is here and why we are alive to investigate it. The cosmic conditions for sustained biological evolution depend on having a low enough rate of significant cosmic radiation events, including magnetar giant flares, supernovae, gamma-ray bursts, and various other phenomena. Earth's specific position has been favorable. Other planets in less favorable positions may have experienced biospheres that were ended by cosmic events that we, in our specific location, have avoided. Now, let's begin to think about what this implies for your sense of cosmic perspective. The classical view of cosmic context placed Earth and the cosmos as somewhat separate, with cosmic events being remote curiosities that did not really affect daily life. Expectation, the classical view. Reality, the revised view based on the careful empirical work of modern astrophysics, is somewhat different. Cosmic events do affect planetary biospheres. The events are rare, but not absent. Earth's history has been shaped, at least in part, by cosmic events that left geological signatures. The relationship between cosmic and biological history is closer than the classical view suggested. This is, in some sense, a more interesting cosmic context than the classical view provided. The cosmos is not just a backdrop. It is, in specific empirical ways, an active participant in the history of any planetary biosphere. The participation is intermittent, with most cosmic time producing no significant effects on any specific planet. But the cumulative participation over billions of years is substantial. Earth's biosphere has, by every available indication, been affected by cosmic events at multiple points in its history. The implications for the broader picture of how life relates to the cosmos are substantial. No one expects, on first thinking about cosmic events, that the cosmos would have so much direct connection to the history of any specific planetary biosphere. No one predicts that the iron in your blood, the carbon in your cells, the very existence of complex life on Earth would all depend on specific cosmic events that occurred long before the solar system formed. Absolutely no one anticipates the way the cosmic and the biological are so deeply intertwined in the actual history of complex life. Expectation? The cosmos is a remote backdrop with no direct relevance to planetary biology. Reality. The cosmos is an active participant in planetary history, with cosmic events including magnetar giant flares contributing to the broader landscape of conditions that have shaped the actual history of any specific biosphere. Hold this thought. We are alive in a cosmos that contains magnetars and supernovae and gamma-ray bursts and various other extreme phenomena. The phenomena affect planetary biospheres at substantial distances. Earth's history has been shaped by such events at multiple points. The relationship between cosmic violence and biological history is, by every available indication, intimate rather than distant. The implications for understanding the broader picture of cosmic life are substantial. What becomes clear is that this is part of what makes magnetars so empirically interesting. They are not just curiosities of stellar physics. They are participants in the broader cosmic history that has shaped, and continues to shape, the conditions under which biological life can exist. The 5 truths we have walked through tonight are real capabilities of real objects in our cosmic neighborhood. The capabilities have been part of the cosmic landscape for billions of years, and will continue to be part of it for billions more. What this leaves us with is a sense of why magnetars matter beyond the specific empirical phenomena. They are part of the broader cosmic context that shapes everything else. The cosmos that contains you is a cosmos in which magnetars exist, periodically produce dramatic events, and contribute to the broader picture of how cosmic conditions constrain biological possibilities. The understanding of magnetars is, in this sense, the understanding of one specific aspect of the cosmic context within which all biological history takes place. Tonight, we're going to address 5 common misconceptions about magnetars directly, because each one is widely repeated in popular discussion, and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that magnetars are about to destroy Earth. The claim has appeared in various viral articles, often timed to coincide with new magnetar observations or new theoretical work. The technical reality is that no known magnetar is at a distance close enough to pose a serious threat to Earth from any plausible event. The closest known magnetar is approximately 9,000 light-years away. Even the most powerful possible giant flare from this object would not produce serious consequences for Earth's biosphere. The probability of a previously unknown magnetar at much closer distance is very small. No one expects, on first hearing the popular framing, that the gap between the headline and the technical situation could be quite this large. No one predicts that the most widely repeated interpretation of magnetar observations would so substantially overstate the actual risk to Earth. Absolutely no one anticipates the way the popular news cycle has compressed a complicated and ongoing scientific discussion into a simple narrative of imminent danger. Before we get started on the second misconception, sit with why the first one persists. Threats to Earth are dramatic. They generate attention. Detailed, technical assessments of actual risk levels are less dramatic but more accurate. The technical framing has, predictably, made less progress in the public imagination than the dramatic framing has. Now, let's begin with the second misconception. The misconception is that magnetars are some kind of exotic, theoretical object whose actual existence is uncertain. The claim sometimes appears in skeptical contexts, with suggestions that the magnetar phenomenon is overinterpreted from limited data. The technical reality is that magnetars are well established as a real class of object. The empirical evidence includes direct observations of approximately 30 magnetars in our galaxy, multiple giant flares with detailed multi-wavelength characterization, theoretical models that successfully predict the observed properties, and connections to other phenomena, including fast radio bursts. The Magnetar class is, by every reasonable measure, empirically well established. Step back, and you can see that this is a clear case where the popular framing of theoretical uncertainty does not match the technical situation. The Magnetar phenomenon has been studied for over 4 decades. The empirical evidence is robust. The theoretical framework is well developed. The objects are not theoretical curiosities. They are part of the standard cosmic inventory. The third misconception is that magnetars are common throughout the cosmos. The claim sometimes appears in popular discussions that suggest magnetars are everywhere, and that planets must be constantly threatened by them. The technical reality is more measured. Magnetars are relatively rare. The total population in our galaxy, including unknown objects, is estimated at perhaps several hundred at any given time. The lifetime of magnetar behavior is only approximately 10,000 years, after which the magnetic field decays to levels comparable to ordinary neutron stars. The cumulative number of magnetars that has existed across our galaxy's history is substantial, but at any given moment the active magnetar population is modest. Expectation: magnetars are abundant cosmic objects that constantly threaten planetary biospheres. Reality: magnetars are rare and short-lived objects, with the cosmic threat being statistical rather than imminent. The fourth misconception is that magnetars are essentially fully understood. The claim sometimes appears in confident popular discussions that present the magnetar phenomenon as a closed topic. The technical reality is that substantial open questions remain. The exact mechanism that produces magnetars during stellar collapse is not fully understood. The detailed mechanism of giant flare events is being actively investigated. The relationship between magnetars and fast radio bursts is not fully resolved. The structure of the magnetar interior continues to be probed through ongoing observations. The field remains, in this sense, empirically and theoretically active. No one predicts, on first encountering modern astrophysics, that the magnetar phenomenon would be both well established as a real class and substantially uncertain in its specific details. No one expects that the same field could have such a robust empirical foundation and so many remaining open questions. Absolutely no one anticipates the way modern astrophysical understanding combines confident knowledge with active uncertainty in this specific way. Notice the turn. The fifth misconception is that magnetar science has reached its limits. The claim sometimes appears in discussions that suggest the most important results have already been obtained and that future work will be incremental. The technical reality is that the next decade of magnetar science is expected to be particularly productive. New facilities, including the Athena X-ray Observatory, the Square Kilometre Array Radio Telescope, and various other instruments will substantially advance our ability to detect and characterize magnetars. New events, including future giant flares, will provide additional empirical input. New theoretical work will refine the framework. The field is approaching a particularly active phase rather than reaching its limits. The takeaway is that this is part of why the current moment in magnetar science is interesting. The combination of established empirical foundations, substantial remaining open questions, and substantial planned new observational capability has produced a particularly productive period in the field. The next major advances, whatever they turn out to be, will likely emerge from this combination of ingredients. Hold this image. 5 misconceptions, each one widely repeated, each one wrong in specific ways. The corrections do not diminish the significance of magnetars as a class of object. The objects are genuinely extreme. The events they produce are genuinely powerful. The implications for planetary habitability are real, but the popular framings, while attention-grabbing, do not accurately represent the technical situation. The actual situation is one of careful, productive work on well-defined open problems, with the timing of major advances being genuinely uncertain. What this leaves us with is a clearer view of what magnetars actually are, not imminent threats to Earth, not theoretical speculations, not abundant cosmic objects, not fully understood phenomena, not a closed scientific topic. The actual situation is more measured and, in some ways, more interesting than any of the popular framings suggest. Magnetars are real, rare, extreme, partially understood objects whose properties are being progressively characterized through careful empirical and theoretical work over decades, with substantial additional progress expected over the coming years. Tonight, we're going to spend a careful pass on what comes next in magnetar science, because the directions of current and future work are worth knowing, and the next decade promises substantial additional progress. Now, let's begin with the first major development. The next generation of X-ray observatories will substantially advance our ability to characterize magnetars. The Athena X-ray Observatory, planned for launch by the European Space Agency in the mid-2030s, will have much higher spectral resolution and much greater collecting area than current X-ray facilities. The combination will allow detailed spectroscopy of magnetar atmospheres and detailed characterization of the X-ray emission during both quiescent and bursting phases. The advances are expected to substantially refine our understanding of the magnetar surface composition, the magnetic field structure, and the dynamics of the magnetar magnetosphere. The XRISM mission, launched by the Japanese Space Agency in 2023, is already providing improved spectroscopic capability for magnetar studies. The X-ray IFU instrument on XRISM has the highest spectral resolution of any current X-ray observatory and can resolve specific spectral features that previous instruments could not detect. The XRISM observations of known magnetars are producing detailed constraints on the magnetic field structure and the surface plasma properties. What this leaves us with is that the second major development involves radio facilities. The square-kilometre array, currently under construction in South Africa and Australia, will dramatically expand the capability for detecting and characterizing fast radio bursts and other magnetar radio emission. The Meerkat array, already operating in South Africa, is part of the Square-Kilometre Array project and is currently producing important results on FRB sources. The KIME telescope continues to operate and continues to detect new FRBs at substantial rates. Pause for a moment. The combination of these radio facilities will substantially advance the empirical study of magnetars at radio wavelengths. The detection of additional galactic magnetar FRB events, similar to the April 2020 event from SGR 1935+2-154, would substantially advance our understanding of the FRB magnetar connection. The detection of additional extragalactic FRBs at increasing distance and increasing precision will substantially advance the use of FRBs as cosmological probes. The third major development involves the multi-messenger approach. Future giant flares from galactic magnetars are expected to be observed simultaneously across multiple wavelengths and possibly through gravitational waves. The LISA mission, planned for launch in the 2030s, may be able to detect gravitational waves from magnetar giant flares under specific conditions. The detection of such gravitational waves would provide entirely new empirical input on the magnetar phenomenon. The combination of electromagnetic observations and gravitational wave observations would constrain magnetar properties in ways that neither approach alone could achieve. The fourth major development involves theoretical work. The cosmology and astrophysics communities are actively developing improved theoretical frameworks for understanding magnetar formation, magnetar evolution, and magnetar events. The frameworks include detailed magneto-hydrodynamic simulations of magnetar dynamics, refined models of crust mechanics, improved understanding of FRB emission mechanisms, and various other theoretical developments. The next decade of theoretical work is expected to substantially refine our understanding of all aspects of the magnetar phenomenon. What surfaces from this is that the fifth major development involves the broader population of magnetars in our galaxy. The current census of known magnetars includes only about 30 objects, but the total population is estimated at perhaps several hundred. The discovery of additional magnetars through surveys with current and future facilities is expected to substantially expand the empirical sample. The expanded sample will allow more detailed statistical studies of magnetar properties and will identify rare types of magnetars that the current sample may not adequately represent. No one expects, on first thinking about the future of magnetar science, that the next decade would offer such substantial expansion of empirical and theoretical capability. No one predicts that multiple major facilities and theoretical developments would be operating simultaneously on the magnetar question. Absolutely no one anticipates the way the next phase of magnetar research may turn out to be one of the more productive in the history of the field. Walk with me through what this implies for the specific questions we have walked through tonight. The first truth about the extreme magnetic fields will be substantially refined by the next generation of X-ray spectroscopy, which will provide direct measurements of the magnetic field strength through specific spectral features. The second truth about the giant flares will be advanced by detection of additional events and by multi-messenger observations of those events. The third truth about the starquakes will be probed more precisely by improved high-time resolution X-ray observations. The fourth truth about FRBs will be substantially extended by the square-kilometre array and other radio facilities. The fifth truth about lethal radius effects will be constrained by improved theoretical modelling of atmospheric and biological responses. Hold this image. The next decade of magnetar science will involve substantial new observational programs, substantial new theoretical work, and substantial new computational capabilities. The 5 truths we have walked through tonight will be tested more carefully than they have been to date. Some of the current uncertainties will probably be partially resolved. Others may persist for further generations. The understanding of magnetars will continue to advance gradually and substantially through the patient work of the broader scientific community. What emerges from this is that this is part of why the current moment in magnetar science is particularly interesting. The combination of the established empirical foundations, the substantial expansion of upcoming observational capability, and the active engagement of large theoretical communities has produced a particularly productive period in the field. The next major advances, whatever they turn out to be, will likely emerge from this combination of ingredients. We are alive at a moment when the empirical study of magnetars is approaching what may turn out to be one of its more dramatic phases. What this leaves us with is a sense of why the current moment matters. We are alive during one of the more capable phases of magnetar research in its history. The work continues, the instruments improve, the theoretical understanding deepens. The extreme objects we have walked through tonight are being probed from multiple directions simultaneously. The magnetars will continue to be studied with increasing care, and the implications for the broader picture of cosmic violence and planetary habitability will continue to be worked out by the active engagement of the scientific community over the next several decades. For the rest of the night, sit with what magnetars actually are: a small, dense sphere of crystalline neutron matter, only about 12 miles across, weighing more than the Sun, spinning on its axis several times per second. A crust of iron and other heavy elements packed to densities thousands of times those of any earthly material, capable of withstanding stresses 10 billion times greater than ordinary terrestrial iron. A magnetic field of 10 to the 15th Gauss at the surface, stronger than anything else in the known cosmos, distorting the structure of the vacuum itself. An internal magnetic energy reservoir greater than the total fusion energy output of a sun-like star over its entire main sequence lifetime. The capacity to release that energy in concentrated bursts lasting only fractions of a second. The capacity to crack its own crust through magnetic stress. The capacity to produce coherent radio emission detectable across cosmic distances. And the capacity, given proximity and direction, to end a planetary biosphere at distances of 1,000 light-years or more. This is what a magnetar is. The 5 truths together describe a single object of extraordinary capabilities, with each capability flowing from the same underlying source. The magnetic field is the engine. Everything else is a consequence. Picture, for a moment, what one of these objects actually looks like in cosmic context. The magnetar sits in space, surrounded by the diffuse glow of the supernova remnant from its parent star's explosion. The remnant, an expanding shell of hot gas thousands of years old, fills a region of approximately 100 light-years around the central object. Within the shell, the magnetar itself is essentially invisible at optical wavelengths, with only the brightest X-ray and gamma-ray emission revealing its location. The surface of the magnetar, 12 miles across, glows with thermal radiation at temperatures of millions of Kelvin. The atmosphere, if it exists at all, is only millimeters thick, composed of plasma so dense and so hot that the standard concepts of atmospheric science do not really apply. Now, let's begin to think about this. The magnetic field structure extends outward into the surrounding space, with field lines threading through the supernova remnant and reaching distances of many light-years. The field, even at substantial distances from the magnetar, is strong enough to dominate the dynamics of any plasma in the region. The radiation environment in the vicinity is intense, with constant X-ray and occasional gamma-ray flux from the magnetar's routine activity. Periodically, perhaps once per several decades, the magnetic field reaches an unstable configuration and reconfigures itself. The reconfiguration releases enormous amounts of energy in the form of a giant flare. The flare propagates outward at the speed of light, carrying its gamma-ray pulse across the supernova remnant, across the interstellar space beyond, and eventually across many tens of thousands of light-years before its intensity decreases below the threshold of detectability. Any planet in the path of the flare receives a brief but intense pulse of radiation. If the planet is close enough, the consequences for any biosphere on its surface can be severe. Slowly, the camera in your imagination drifts outward. It leaves the room where you are sitting. It rises above the building, above the city, above the planet. It travels outward through the solar system, past the planets, past the Oort cloud, into the interstellar space beyond. It pushes further, past the nearby stars, into the regions of the galaxy, where the known magnetars reside. The 30 or so known magnetars are scattered across the galactic disk and bulge, with most of them concentrated in the inner regions of the galaxy, and a few in the spiral arms. The camera approaches one of the magnetars. The surrounding supernova remnant becomes visible, an expanding shell of hot gas glowing in X-rays and optical wavelengths. The central magnetar is essentially a point source against the background of the remnant, with its intense radiation dominating the high-energy spectrum of the entire system. The magnetic field structure, invisible to direct observation, threads through the system and shapes the dynamics of everything within it. The camera moves on. It passes additional magnetars, each one a small, extraordinary object in its own supernova remnant. It surveys the full known magnetar population, then continues outward toward the regions of the galaxy, where magnetars are likely to exist but have not yet been identified. The total population of magnetars in the galaxy, including the unknown objects, may be several hundred or more, with each one a similarly extreme object capable of similarly extraordinary events. The camera turns around and begins the long drift back, past the magnetars, past the nearby stars, past the Oort cloud, past the planets, past the Earth, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room on this night is alive on a planet that has, by every available indication, never been close enough to a magnetar giant flare to suffer serious consequences. The probability of such an event affecting Earth in any specific time window is very small. The cosmos around you contains the extraordinary objects we have walked through tonight, but the cosmos is also large enough that the extraordinary events these objects produce are usually distant enough that we observe them as remote astronomical phenomena, rather than as local disasters. What this means for how you experience the night sky outside is subtle. The stars you see are not magnetars. Magnetars are too dim at optical wavelengths to be visible to the naked eye, and they are mostly located in regions of the galaxy that are obscured by interstellar dust. The visible stars are ordinary stars, going through their ordinary stellar evolution, with no special connection to the magnetar population. But the cosmic background contains, by every available calculation, approximately 30 known magnetars in our galaxy, and many more unknown ones, each one a small, extraordinary object capable of the 5 capabilities we have walked through tonight. The cosmos that contains you is, in this sense, both serenely beautiful at the scales we can observe with our eyes, and quietly violent at the scales that require specialized instruments to detect. The two pictures coexist. The visible night sky is genuinely peaceful. The high-energy cosmic background contains, hidden in its faint X-ray and gamma-ray flux, the activity of objects whose capabilities exceed anything we can produce in any laboratory. Both pictures are part of the cosmic reality. Both deserve careful attention. There is no need to hold all of this in your mind. The 5 truths will keep their shape whether you remember the details or not. The magnetars in the galaxy will continue their activity, producing routine starquakes and occasional giant flares, and the various other phenomena we have walked through tonight. Most of those events will be detected only by specialized X-ray and gamma-ray observatories. A few will produce notable empirical results that will advance our understanding of these objects. The work of magnetar astronomy continues, with substantial progress being made every year. The cosmos that contains your sleeping body is the same cosmos that contains the magnetars. The extreme objects are part of the cosmic landscape. The cosmic landscape has been here for billions of years and will continue for billions more. We are alive at a moment when the empirical study of magnetars is one of the more productive areas of modern high-energy astrophysics, with substantial new results expected over the coming decade as the next generation of X-ray and radio facilities come online. Sleep can come whenever it wants now. The story has done its work. The magnetars are out there in the galaxy, quietly carrying their extreme magnetic fields and occasionally producing the dramatic events we have walked through tonight. The cosmos is what it is. You are part of it. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.